students, how are you? In the today's class, we are going to start the topic equilibrium. Before starting this chapter, we need to understand the term equilibrium. What is the meaning of the equilibrium? Have you ever seen a triplet artist that is walking on a rope? You will see there are so many factors that would influence its balance, but yet it would maintain its balance like temperature, pressure, gravity. There are so many factors that would influence its balance, but still she maintains its balance. Now, this state of balance is your equilibrium. Within a system where opposing forces are equal, that the stage is your equilibrium. Now let's understand with the help of this beam balance. There are two weights on the opposing sides. If they are equal, so what we are observing, the opposing forces are equal. Now this state is your balance state. This is your equilibrium stage. Now let's understand this equilibrium in the physical process. There are so many physical processes in the chemistry like melting, freezing, boiling. We all know about it. But how the equilibrium would exist in these physical processes, let's understand. Firstly, we are going to understand the solid-liquid equilibrium. As we know, when the solid starts converting into the liquid, that process is melting. We know about it. But how the equilibrium would exist in it, let's understand. Suppose you have an insulated flask in which you have kept some ice and some water in it. The mass of the ice and water that is constant initially, as we know that. Okay, so the mass of ice and water is constant initially in this insulated flask at 0 degrees Celsius temperature and at 1 atmospheric pressure. What you are observing? You are observing that ice starts converting into the water, into the liquid water. See, we are expecting that at 0 degrees Celsius temperature, only the water must be present. But we are observing that both the phases are present like ice and water at the 0 degrees Celsius temperature. What is the reason behind this? At 0 degrees Celsius temperature, initially ice starts converting into the liquid water. But this liquid water cannot escape out from this insulated flask. So it starts again losing its energy and again colliding and stuck with the ice molecules. So we would observe after some time the rate of melting and the rate of freezing, like ice to water conversion and the water to ice conversion. These two rates would become equal and we can say the mass of the ice and water would become constant. It is like equal at that particular temperature. Now this stage is known as your equilibrium. So at the equilibrium, both the phases are present, solid and liquid. We are observing that at equilibrium, we are expecting that it is static in nature. Static in nature, like molecules are like still. But at the equilibrium, they are not still. This equilibrium is dynamic in nature. Dynamic in nature, what is the meaning of this? Like ice molecules continuously converting into the liquid water and the liquid water continuously converting into the ice molecules. They are stucking and colliding against with the ice molecules. So we are observing that at equilibrium is dynamic in nature. Both the opposing processes are occurring simultaneously. Now rate of melting and rate of freezing both are equal in nature here we can understand. So now this is the equilibrium that we can understand in the solid liquid equilibrium. You can easily understand this water molecule which is present in this insulated flask, the H2O molecules. The rate of ice to water conversion and water to ice conversion, that is equal. Mass of ice and mass of water at a particular temperature and pressure, that would remain as constant. So at the melting point, the substance in solid phase, that is in equilibrium with the liquid phase. Generally the melting point, what is the definition? At a particular temperature when the solid starts converting into the liquid. But now we can understand at the particular temperature, the substance in solid phase is in equilibrium with the liquid phase. Its liquid phase, that is known as your melting point. That particular temperature where both the phases are present and we are observing that solid to liquid conversion rate and the liquid to solid conversion rate, both are equal. That is your what? That is your melting point. And we can easily understand why the temperature would remain as constant, because both the processes are occurring simultaneously, and the latent heat concept that we have already studied in the previous classes. So we can easily understand the temperature is constant, both the phases are present. That temperature is your melting point, or you can say the freezing point of that particular substance. Now, next is liquid vapor equilibrium. See students, as you know about the evaporation process, the condensation process, what is the meaning of evaporation, the liquid to vapor conversion? What is the condensation, the vapor to liquid conversion? Okay, but now how the equilibrium would exist in these processes? Let's understand. Suppose you have this beaker, and in this beaker you have what? You have this watch glass in which you have filled some water. Initially what we have done, from this beaker we have used the anhydrous calcium chloride. This anhydrous calcium chloride that would remove all the moisture which is present in this beaker. Okay, now here we have this watch glass in which we have filled this water. We are observing that a manometer is connected here and the mercury is filled in this manometer. The mercury level on both the limbs, that is equal. Now what we are observing, after some time the liquid starts converting into the water vapors. Okay, these water vapors would apply some pressure on this mercury. What would happen when they would apply some pressure on here on this left hand side? We would observe that the mercury on the right hand side, its level would be increases because the pressure is applying from this left hand side. So we are observing that the mercury level in the left hand side goes down and the mercury level in the right hand side goes up, because we have applied a pressure by these water vapors. And after some time we would observe that the mercury level on both the sides would become constant. Why? Because the pressure we are applying here, that is also constant. Why this pressure would become constant? Because we are observing that from water to water vapors are converting, but these water vapors cannot escape out from this beaker. So we are observing that these water vapors would condense back, they would lose their energy and would condense back and converting into the liquid. So we are observing that rate of evaporation, and the rate of condensation, that is equal. At the equilibrium you are observing that rate of evaporation and rate of condensation, that is equal. This is known as your what? This particular temperature at which both the phases are present, liquid and vapor phase are present, and both the evaporation and condensation process occurring simultaneously, that stage is your equilibrium stage. So the rate of evaporation and rate of condensation would become equal. Now here we can easily understand, at a given temperature the temperature would remain as constant, and it is known as your equilibrium vapor pressure of water as well. See students, we can easily understand, suppose as we know at 100 degrees Celsius temperature, the water and water vapor both are in equilibrium with each other. The water and water vapor both are in equilibrium with each other. What is the meaning of this? At 1 atmospheric pressure and at 100 degrees Celsius temperature, both the phases are present. The meaning of this, the water to water vapor conversion rate and the water vapor to water conversion rate, that is equal. These rates are equal, and we are observing that their concentration would become, their amount would become constant at the particular temperature. So at the equilibrium both phases are present, and we would observe the pressure exerted by the water molecules, the pressure exerted by these water molecules at a given temperature, that would remain as constant. Now this is known as your equilibrium vapor pressure of water. See, we have already listened about it, the vapor pressure. What is the meaning of the vapor pressure? The pressure applied by these vapors. Now at which condition? At the equilibrium condition, whatever be the water vapors are present in this closed beaker, the pressure they are applying on this liquid water surface, that is known as your what? That is your equilibrium vapor pressure of that water. So we can easily understand the pressure exerted by the water molecule at a given temperature, that is constant, and this is your equilibrium vapor pressure of the water. See students, when the water starts converting into the vapor form, so what he is applying? He is applying some pressure on that molecules. When the water vapors, they are converting into the liquid form, what they are applying? They are applying some kind of pressure on these liquid surfaces. So we can easily understand the pressure meaning over here. Now the water and the water vapor are in equilibrium position at atmospheric pressure and at 100 degrees Celsius in a closed vessel. So we can easily say this is the what? This is the boiling point of that particular water substance. At a particular temperature, both phases are present. Equilibrium is not static in nature, it is dynamic in nature, as we can easily understand. Okay, it is dynamic in nature. Both processes are occurring. Now solid vapor equilibrium. Next is solid vapor equilibrium. If we place solid iodine in a closed vessel, suppose in this closed vessel there is a I2 in the solid form. Now after some time, I2 solid, what is the color for this? This is colorless initially. Now after some time, what we are observing, that this vessel, it will be get filled up with the violet vapors. Why it will filled up with the violet vapors? Because we would observe that it would gain some energy and it will start converting into which form? I2 solid starts converting into the I2 vapor form. In the I2 vapor form, what is the color? The violet color is there. So we are observing that initially it is colorless. Now after some time in the beaker, you have this violet vapor. So violet vapor color intensity is going to be increased. But after some time, this violet vapor color intensity, that would become constant. Why it is so? Because we are observing the opposing process starts after some time. Like I2 vapor form to solid formation, that will also occur. Okay. So here we can understand. Let me take some pause and then I will start. Okay, after some break we are present here. Now we can easily understand this complete beaker. It has a constant color. Constant color, what is the meaning of this? Initially the colorless, after some time the violet color intensity is going to be increased. But we are observing that I2 vapor form to solid conversion, again it would start. So the color intensity is not going to be so much increased. It is again converting into the colorless form. So the color would become constant over here. So we can easily understand at the equilibrium both the phases are present. The solid and the vapor form are present over here. Okay. Now this is the solid vapor. What? Solid vapor equilibrium. You can say the rate of sublimation, and the rate of condensation. The rate of sublimation and the rate of condensation, that is equal. Now this is your equilibrium stage. Equilibrium involves dissolution of solid into the liquid. Now let's understand about this, how the equilibrium would exist, the solid substance dissolution in a liquid. See students, all of you know about the saturated solution. What is the meaning of the saturated solution? Saturated solution means what? The temperature at which a maximum amount of solute can be dissolved in a given amount of solvent. That is known as your saturated solution. You can easily understand that at a particular temperature, the maximum amount of solute that you can dissolve. After that, you will not be able to dissolve that particular solid substance amount in that solvent. Now your solution is going to be very saturated. This is the meaning of this one. We can easily understand. Now here, let's understand with the help of some example. Suppose you have this beaker in which you have some water is present over here. Now you are adding some sugar crystals into this water. What would happen? You will use a stirrer here. With the help of stirring, what you are doing, you are trying to dissolve the sugar molecules in this water molecules. Okay, the sugar molecules, they are start keeping dissolving into these water molecules. We are observing after some time, some sugar crystals would remain at the bottom of the beaker. Some sugar crystals are present over here in the crystallized form. They are present in the crystallized form. They are not present in the dissolved form. So here we are understanding that there is an equilibrium that is existing between these sugar molecules which are in the dissolved form in the water and which are in the crystal form. So you can say the sugar in the solution form, the dissolved form, and in the undissolved form at the bottom of the beaker, they both are in the equilibrium stage. So what is the meaning of this? we think that some of the sugar which is present at the bottom of the beaker, that this stage is like static stage. But the equilibrium is dynamic in nature. Sugar which is present in the dissolved form and sugar which is present in the crystallized form. Continuously molecules are going from dissolved to what? Dissolved to crystallized form and crystallized form to dissolved form. So we can easily understand molecules are vibrating from here to here. Okay. From here to here they are vibrating easily. Okay. Now equilibrium is dynamic in nature. We can easily understand. So at a particular temperature, the concentration of a solute depends upon the temperature as well. See, if we are increasing the temperature, in this stage, if we are increasing the temperature, the sugar molecules, they again starts dissolving more. Now your equilibrium will be disturbed. So these equilibrium condition, this concentration would depends on the temperature. Always remember this condition. Now here you can understand, this is my saturated solution. Solute I am adding in this solvent. Some will be dissolved and some will remain as in crystallized form. Okay. So see, when you say that my solution is saturated. Saturated means, what is the meaning of this? You are not able to dissolve more solute in that. So the reason behind that is what? The reason behind that is your equilibrium. Equilibrium has been exist over here. Equilibrium already exists between the dissolved molecules and in the crystallized form. They are starts converting to this form. Okay. Now here, gases in liquids, how the equilibrium would exist in this form. The best example is what? Soda water bottle. See students, whenever you will see the Pepsi, the Coca-Cola water or the water bottle there are, when you are opening that lid point, what would happen? The carbon dioxide gas which is present in it, that would comes out, fizzes out rapidly. Why? Because carbon dioxide gas which is present in that soda water bottle, it is just dissolved in it with some pressure. When you are just opening that lid, what would happen? You would observe that atmospheric pressure is also working. So the atmospheric pressure which is working over here, what would happen? It would apply some pressure over here. So you would observe some carbon dioxide gas which is present here, that would also apply some pressure and that is trying to be escaped. So now let's understand how the equilibrium would exist in that soda water bottle. In the soda water bottle, if you will see carefully, what is happening actually, in the soda water bottle, you have this Pepsi, Coca-Cola water bottle is there. You have this liquid in which, in this liquid water, the carbon dioxide gas is present here in this liquid. It is in the dissolved form. Now some carbon dioxide will present in the gaseous form. It is dissolved already in this water and some is present in the gaseous form. Why it is present only in the gaseous form? You will see there is some gap, some spaces left in the soda water bottle top form. What is present there? There is some carbon dioxide gases present there. So once you are opening the lid, now before opening the lid, what is actually happening? Once you are applying so much pressure and the carbon dioxide gas which is present in this atmosphere, you are applying so much pressure, and when it starts keeping dissolving into the water, what is happening actually? Some of that form in the dissolved form, some would remain in the escape form because the maximum amount that has been dissolved, so some amount would remain in the gaseous form. So you would observe the carbon dioxide which is present in the gaseous form in that space and the carbon dioxide which is present in the dissolved form, okay, they are maintaining an equilibrium with each other. Okay, now once you are opening the lid, what is happening? Atmospheric pressure is working over there. So in resultant to this, some of the liquid molecules, some of this gaseous molecules which are present in this space, they are also applying some pressure. They would also apply some pressure. What would happen? The equilibrium which is present over here, that would be disturbed. Once this equilibrium would disturb, what would happen? Some liquid which are some in this liquid, whatever be the carbon dioxide gas in the liquid form, that is also escaping out. So the equilibrium would disturb, and now the again equilibrium would reach Once both the phases would become equal, like carbon dioxide present in the gaseous and dissolved form, when they would become equal, now again equilibrium you can achieve by this way. So you can easily understand why this fizz sound is there. At a given pressure, there is an equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid. The mass of a gas dissolved in a given mass of solvent at a given temperature. See students, there is some law that is applied by the Henry. Henry is saying that the mass of gas that is present in a given amount of solvent that at a particular temperature, that would depend, is directly proportional to the pressure of the gas above the solvent. Now let's understand. Suppose in this beaker you have this solvent and you are applying over here this gas. These gaseous molecules which are just present in this, that would be dissolved in this liquid, will depend on which condition, how much pressure you are applying. The more the pressure you are applying on the gaseous molecules, the more the gaseous molecules would start dissolving into the liquid. Clear? Now the mass of the gas that is directly that would present in the given amount of solvent, it is depend on the pressure. The more the pressure of the gas that will be applied, the more the mass of the gas would be dissolved. So M is directly proportional to the P. M is equals to proportional sign you will remove. So proportionality constant K will be there. Kp. K is proportionality constant, depends upon the temperature. K is what? That is a proportionality constant. It will depend on the temperature. So the mass of gas which is present here will depend, which will be dissolved in the given amount of solvent, will depend upon the pressure. The more the pressure you would apply on the gas, the more the mass of the gas would dissolve in that solvent. Okay. Now here, that was the Henry's law. Now equilibrium in the chemical process. All that we have understood about the physical process. Now how the equilibrium would exist in chemical process, let's understand. See students, you have seen so many irreversible reaction and a reversible reaction. Irreversible reaction that occur only in one direction. Reversible reaction that occur in both the direction, that is your reversible reaction. A reaction that occurs not only in the forward direction but also in the reversible direction, that is known as your what? That is your reversible reaction, not only in the forward but also in the backward direction. Like you can easily understand, suppose you have this CaCO3, it starts heating and forming what? CaO plus CO2. After some time you are observing that the CaO plus CO2, they are reacting and forming what? They are reacting and forming CaCO3. So we would observe that CaCO3 to CaO plus CO2, CaO plus CO2 again forming the CaCO3. So the equilibrium would exist in this reversible reaction. Equilibrium means what? The rate of forward reaction to rate of backward reaction. CaCO3 to CaO conversion and CaO to CaCO3 conversion, when this rate would become equal, that is known as your equilibrium stage. Okay. Now here we can easily understand reversible reaction. We all are clear that not only occurring in the forward but also in the reversible direction, that is your reversible reactions are there. Now you can easily understand, suppose you have a reaction A plus B. They are two reactants, they are reacting and forming what? The product C and D. After some time the C and D products are reacting. For the reversible reaction, these are my reactants. For the reversible reaction, these are my reactants, and they are reacting and forming the A and B. They are reacting and forming the A and B. Now this is my complete reversible reaction. You can easily understand. So here we can understand, initially we have started with the A and B reactants. They are reacting and forming the product C and D. After some time, for the reversible reaction, these are my reactants. They are reacting and forming the A and B. After some time, we would observe that rate of forward reaction and the rate of backward reaction, that would become equal. Like A to B reacting and forming C and D, C to D reacting and forming A and B. When this rate would become equal, and you can say the concentration of these species, that would become constant, that is known as your equilibrium stage. Okay, so here equilibrium can be achieved in the chemical reactions as well. Graph between concentration and time, let's understand about it. Initially the reactant concentration was very high. After some time, the reactant concentration starts decreasing, and we would observe the product concentration starts increasing, and after some time both the concentration would become constant. Now this stage is your equilibrium stage. Now let's understand concentration on the y-axis and time on the x-axis. Now let's understand about it. A and B concentration is very much high initially. After some time its concentration starts decreasing. C and D concentration initially was very low. After some time it starts increasing, and after some time, at a time would come, a stage would come where both the concentration would become constant. And when this would happen, this is known as your equilibrium condition. This is your what? Equilibrium condition, where both the concentration would become constant, not equal. So many students would get confused that concentration would become constant means equal. Constant means not equal. They are constant means their value is not changing. Now some students will tell me, now this is in static process. No, it is dynamic in nature. Dynamic in nature means what? Suppose at the equilibrium, the 2 moles of A are there, 2 moles of B are there, and 4 moles of C and 4 moles of D are present over here. So what is happening at the equilibrium? They are not in a static molecule form. Equilibrium is the name of dynamic. So 2 molecules of 2 moles of A are reacting with the 2 moles of B. They are forming the 4 moles of C and 4 moles of D. And at the same time 4 moles of C and D, they are reacting and forming the A and B. Getting my point, student? Now this is my equilibrium stage where concentration would become constant and rate would become equal. Now the graph between the rate and the time, let's understand about it. You are taking rate on a y-axis and time on an x-axis. What is happening actually? The rate of the forward reaction and the rate of the backward reaction would become equal. Initially, as we know, which process is in high amount? A plus B are reacting and forming the C and D. The forward reaction rate, the forward reaction speed will be high. Okay, the forward reaction speed will be high. So initially the forward reaction is very high. After some time the forward reaction would decrease and the rate of the backward reaction would increase, and after some time both they would attain a stage where both the rate of forward reaction and the rate of backward reaction, that is equal at a particular temperature. Now this is my equilibrium. This is my equilibrium where both rate of forward reaction and rate of backward reaction, that is equal. Okay, so we can easily understand A to B formation, A to B forming C and D, C and D reacting and forming A and B. Their concentrations are constant, that is not equal. You can understand 2 mole, 2 mole, 4 mole, 4 mole, that is constant, not equal. Rates are equal. The speed at which they are forming products, the speed at which they are C and D are reacting and forming A and B, that is equal. Okay. Now here, decomposition of N2O4 in a closed vessel. Now we can easily understand how the equilibrium is existing in a chemical reaction. Let's understand. Suppose you have this N2O4 that is colorless in nature. When it starts heated it up, then what is happening? N2O4 that would form the NO2, which is reddish brown in color. If it is a reversible reaction, what would happen? NO2 would again form the N2O4. Now let's understand how the temperature would play an important role in this chemical reaction and how the equilibrium would exist over here. See students, we can easily understand. Suppose you have taken this N2O4 in a glass bulb. In a glass bulb you have taken this N2O4, or you can say in a test tube you have taken this N2O4. And in a beaker which has already ice present over here. In this ice contacted beaker, you have placed a test tube in which you have N2O4, which is colorless in nature. Okay. Now here, it is like colorless in nature. Now At 0 degrees Celsius temperature, you are observing this condition. Your N2O4 is colorless in nature when you are keeping in contact with the ice. Now, if you are taking this test tube and you are placing this test tube in this beaker which is placed at the room temperature, and here the water is present over there. Okay, now you are placing this test tube over here at the room temperature. What is happening? Your test tube color in which the N2O4 is present, its color starts changing from colorless to it is acquiring reddish brown color. We can easily observe the reddish brown color, and after some time this color would also become constant. Why it is so? Because colorless to reddish brown it is happening when you are increasing the temperature. Reddish brown color is there. After some time this reddish brown color is diminishing and it is forming the N2O4, the colorless, so the color would become constant over here. But if you are increasing the temperature more, if you are increasing the temperature more than room temperature, then what would happen? If you are increasing more than room temperature, then the equilibrium would be disturbed. More NO2 will be formed. If more NO2 will be formed, now you can understand, if you are placing this test tube in this beaker where hot water bath is present, a very hot water is present, more than 25 degrees Celsius temperature is there, its color is very much reddish brown. So now you can easily understand how the equilibrium is existing in this chemical reaction and how the equilibrium would disturb if you are increasing the temperature. Suppose you are suddenly decreasing the temperature. Suppose you are placing this hot water test tube in this ice contacted. Its color would become diminished. Okay, it is like colorless in nature. When you are at the room temperature, both the phases are present, N2O4 and NO2, and they have a constant color of this reddish brown. Getting my point, student? So here we can understand in this chemical reaction how the equilibrium would be exist over here. Now the dynamic nature of the chemical equilibrium. We can easily understand at the equilibrium we observe and we feel that all the things are static in nature, but they are not static, they are dynamic in nature. So now this dynamic nature you can understand with the help of some graph and with the help of some activity you can understand. Suppose you have the reacting species like nitrogen gas, hydrogen gas, they are reacting and forming the ammonia, okay? And if it is reversible in nature, then what is happening? What would happen after some time? Ammonia would start converting and forming nitrogen and hydrogen. This is a reversible reaction, okay? Now here in the place of this H2, you are placing the deuterium over here. This is nitrogen plus deuterium and it would form what? ND3. Now here after some time this ND3 would again form the nitrogen and deuterium. The equilibrium that has been achieved by this chemical reaction already. So you have two separate mixtures in which you can see that the ammonia and ND3 is present. They have separately acquired their equilibrium stages. The separate reaction mixtures are there. Once you are combining these separate reaction mixtures with each other, what would happen actually? If the equilibrium is dynamic in nature, what we need to prove? We need to prove that this reaction that has already achieved the equilibrium, the rate of forward to rate of backward is equal. Nitrogen, hydrogen at the equilibrium continuously they are reacting and forming ammonia, and ammonia is continuously forming nitrogen and hydrogen. Okay, we are expecting this thing at equilibrium. We need to prove this thing that molecules are still separating, still combining, like nitrogen atom is separating from N2 molecule, hydrogen atom is separating from hydrogen molecule, it is forming NH3 molecule. We need to prove this thing. Okay, so what we have done, we have taken the another reaction mixture, the another reaction in the place of this hydrogen, you have placed the deuterium isotope. As we know, hydrogen has 3 isotopes, 1H1, 1H2, 1H3. So this is my deuterium 1H2 isotope is there. Okay. Now here what we are observing, that has formed the ND3. This reaction has already achieved the equilibrium, like nitrogen atom from this N2 molecule is separating this deuterium as well, and they are forming at the equilibrium, they are in dynamic in form. So we need to prove So what we have done, we have mixed these two reaction mixtures with each other. What we are observing? We are observing that in the equilibrium mixture, what type of species you have? You have nitrogen, hydrogen, ammonia, you have deuterium, N2, ND3, and now we are observing in the reaction mixture you have NH3, you have NH2D, NHD2, ND3. Now you can easily understand these two different species which are coming. Why they are coming? Because we are observing that at equilibrium atoms are definitely still separating from this molecule. Nitrogen atom is separating from this N2, hydrogen atom is also separating from this H2, deuterium atom is also separating from this D2. What would happen? NHD2 molecule they are forming, NH2D they are forming, ND3 is also there. So this proves that your atoms are separating from that molecule and they are forming the different new species. So that's how we need to understand, and we have understood how this dynamic equilibrium would exist in the chemical equilibrium process, how the dynamic nature is there. Now there is a very important topic, that is law of mass action and equilibrium constant. What is the meaning of the law of mass action? Before starting this topic, I think we need to take a pause. We should start in a next lecture. Before that, I hope you all are clear how the equilibrium would exist in the physical process, in the chemical process. How much you have liked, just please like and comment on my YouTube channel. Please like that one and subscribe as well. If you are finding that more video lectures, the more topics you want to understand, you can just message on me. Thank you. We are going to upload this next lectures very soon, very early. Okay, thank you.